Welcome to this first video about semiconductor physics. During this course, you will learn about the properties of a semiconductor as a photoactive material for solar cells. I will introduce you to the topics that we will cover during the coming four weeks. Semiconductors are materials that are widely used for several applications. We can find them in electronic devices such as diodes, transistors, or integrated circuits. But for us, they play a crucial role as active materials in solar cells. But what is a semiconductor? Let's define this term. We will do this by looking at important material properties that define a semiconductor. When we look at materials' ability to conduct electricity, they are generally divided into three classes: conductors, semiconductors, and insulators. A semiconductor is a material whose electrical conductivity is lower than the one of a conductor, but higher than that of an insulator. One example of a semiconductor material is silicon. Solar cells made of silicon dominate the photovoltaic market. Therefore, we will focus our attention on silicon as an example of semiconductor material. We will explain its properties and use this material to describe the working principle of a solar cell. A way to control the performance of a silicon-based device is doping the material. Doping is a process to manipulate the concentration of mobile charges in a semiconductor. This is done by replacing silicon atoms in the lattice by atoms of a suitable element. Doping will increase the electrical conductivity of a semiconductor. Common dopant elements for silicon are boron and phosphorus. The presence of boron or other group 3 atoms is known as p-type doping because it increases concentration of positive charges. The use of phosphorus or other group 5 atoms is called n-type doping because it increases concentration of negative charges. We will go further into the consequences of doping in the coming week. P means extra positive charge carriers. N means extra negative charge carriers. In order to describe the properties of a semiconductor, we make use of energy band diagrams. They are useful representations of the allowed energy states for electrons in a material. We will use them to describe the main properties of silicon and all the properties involving transport, generation, and recombination of the charge carriers. Since the accurate form of these diagrams is rather complex, for simplicity, they are usually represented as shown here. I will explain the meaning of this diagram in the coming week. Since electric current only arises from a net movement of charges, during the first week we will discuss the mechanisms of charge transport. In a semiconductor, we distinguish transport based on drift and diffusion of carriers. Drift occurs in response to an electric field. Diffusion, on the other hand, is based on thermal motion and is driven by a difference in carrier concentration at different places in the device. Both of these processes are important for understanding how charges move around in a solar cell. This topic will conclude our first week of lectures. The second week we will dedicate to 2 very fundamental processes for photovoltaic conversion: generation and recombination of charge carriers. Let's briefly introduce these concepts. In most semiconductors, the atoms are kept together by covalent bonds. The covalent bond is formed when 2 atoms share 2 electrons, each atom contributing with 1 electron. We call these electrons valence electrons, and they are immobile while forming a bond. The energy states of valence electrons are in a valence band of allowed energies. Through different forms of excitation, such as temperature increase or illumination, those electrons can be liberated from bonds through a process known as generation. In band diagram, this process can be visualized as electron moving from a state in the valence band to a state in the conduction band. Excited electron leaves a vacant place in the valence band, and this vacant place is called a hole. You will learn a lot about this process and how it works in a solar cell. Generation is in high competition with its opposite process, recombination. This essentially means that excited electrons return to form covalent bonds. Band diagram is a good means to visualize this process. There are 3 main mechanisms of recombination, and you will learn all about each of them in future videos. This will conclude the 2nd week on semiconductor physics. In the 3rd week, you will learn what happens when we put a p-type semiconductor and n-type semiconductor together. This forms a p-n junction, the extremely important component in semiconductor physics. This is the most important building block of most solar cells. P and n-type doped layers are commonly applied together in a device. There are several reasons behind this choice. First of all, as we said, doping enables us to manipulate the concentration of charge carriers. We can use boron atoms to make silicon p-type. This increases the concentration of holes. Besides, we can use phosphorus atoms to make silicon n-type. This increases the concentration of mobile electrons that occupy energy states in the conduction band. In the coming week, you will learn what happens when these 2 materials come together. The p-n junction, as shown here, is important for separating photo-generated electrons and holes. The p-n junction's properties change when voltage or illumination is applied. You will learn how these effects take place in a silicon-based p-n junction and how the junction can be used as a solar cell. p-n junctions are not the only junctions that are present in a solar cell. Photoactive layers are also placed in contact with metals. This will be one of the main topics of the final week of semiconductor physics in this course. In this week, you will also explore other advanced semiconductor topics like the recombination current, J-naught, and the junctions formed between 2 different semiconductor materials, so-called heterojunctions. Let's begin to look at the configuration of common solar cells. Generally, a moderately doped semiconductor layer is sandwiched between other highly doped layers. As we mentioned before, this is done to promote separation of photo-generated charge carriers within the device and their collection. A solar cell has to be connected to the external circuit, where the electric current generated by solar cell can do a useful work. This is done by applying 2 metallic layers, one on the front and one at the back of the device. They are called front and back contacts. Their presence is necessary to extract photo-generated electrons from a solar cell. During last week, we will understand what happens at the junction of a metal and a semiconductor. We will start with an explanation of the energy band structure of metals. By doing so, we will introduce the concepts of the vacuum level, work function, and electron affinity. Then, we will explain to you how to make a metal semiconductor junction and what are its implications on device performance. Lastly, we will focus on the difference between ohmic and Schottky contacts. In this video, I introduce the main topics of the semiconductor physics section of this course. This will take 4 weeks. At the end of these 4 weeks, you will be an expert in semiconductor material properties. You will understand transport, generation, and recombination processes in semiconductors, the p-n junction, and the metal semiconductor junction. With this knowledge, you will be on your way to becoming an effective solar energy engineer.